I'm Natalie Brunson, and you're watching the Atom Crash Course. The atom contains a positively charged nucleus made up of protons, discovered in 1911 by Rutherford, and neutrons that were discovered in 1932 by James Chadwick. The space outside the nucleus is occupied by negatively charged electrons, which are approximately 1,835 times smaller than protons and neutrons. That's why these are big and these are little bitty ones. Relative atomic mass is the mass of a chemical element expressed in atomic mass units. It is approximately equivalent to the number of protons and neutrons in the atom. A mass spectrometer is used to determine the relative atomic mass of an element from its isotopic composition. You read the results by interpreting the graph generated.
Atomic number is the number of protons in the atom as well as its number on the periodic table. Atomic symbol is the element symbol on the periodic table. Mass number is the total number of protons and neutrons in the atom. An isotope occurs when there are forms of the same element with different number of neutrons. This is the nuclear symbol, where X is the nuclear symbol, A is mass number, and Z is atomic number. Once you know all this, you can begin to work calculations involving non-integer relative atomic masses. For example, boron has 2 naturally occurring isotopes with natural abundances listed in the table. In order to find the relative atomic mass of boron, you multiply each isotope by its natural abundance percentage and add it together.
An emission spectrum is produced at an atomic level because the electrons jump between energy levels. Based on Bohr's research, the atom consists of a positively charged photon in its center, around which negatively charged electrons orbit. At higher energies, the electrons begin to exceed the limits of the atom and become free electrons.
The Bohr model introduced the idea of a main energy level, described by N, which is the principal quantum number. Each main energy level can hold a maximum number of electrons given by 2n squared. So this is why the electron capacity for N1 is 2. For N2 is 8 and continued.
Energy level 1 has sublevels of S. Energy level 2 has sublevels of S and P. Energy level 3 has sublevels of S, P, and D. Energy level 4 has sublevels of S, D, F, and P. As seen on the model, energy must be continually flowing throughout the atom to maintain these E configurations. Sublevel S has 1 orbital. Sublevel P has 3 orbitals. Sublevel D has 5 orbitals. Sublevel F has 7 orbitals. Orbitals are areas where finding an electron is likely. It doesn't mean that these particles follow this path. It's more like these lines that represent orbitals are like boundaries, and you're likely to find an electron within them, between it and the nucleus. As this number of the energy level increases, so does the energy it takes to get there. So this electron would have way more energy than this electron would have. Okay, so wavelength, color, and energy are all related. In this little red area, the wavelengths are much longer. They're about 700 nanometers, and they're very low in energy. And over here in the purple, they're much shorter. They're like 400 nanometers, and they're much higher in energy. And beyond this, also there are waves that aren't like on the visible spectrum. They're there, but you just can't see them. Like radio waves are over here, and ultraviolet light is over here. And they're super high in energy and super low in energy. The emission spectra of hydrogen differs from the continuous spectra visually. The electromagnetic spectra consists of radio waves, microwaves, infrared, visible waves, UV waves, X-rays, gamma rays.
Electromagnetic radiation is radiation from the electromagnetic spectrum in which electric and magnetic fields vary simultaneously. The hydrogen emission spectrum is the spectral series of wavelengths throughout the hydrogen atom. This is what it looks like. These lines are due to the electron releasing energy in the form of photons. The hydrogen atom specifically releases energy at the specific points along the emission spectrum. These lines appear because of the jump of energy from the N3 to the N2 and N1 energy levels, as seen here. These are examples of the types of orbitals electrons are held in. This is the s orbital, this is the py orbital, this is the px orbital, and this is the pz orbital. These graphs represent theoretical planes that control the direction.
The proper way to write an electron configuration is to write from lowest to highest energy levels, as demonstrated in the Aufbau principle. For example, the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. While writing, remember that orbitals can only hold 2 electrons, and orbitals fill up singly first before doubling, as stated in Hund's rule and the Pauli exclusion principle.
Alright, so the reason we chose to do a video like this is because we're both visual learners, and we like the interaction of a video more than like a PowerPoint or just notes or something, and we did a video instead of a presentation because we're hoping that this is going to minimize little indiscrepancies, and we're hoping for the best. So
some unique skills we demonstrated throughout our project were our ability to edit videos and make models. Thanks for watching, and see you next time on Crash Course.